Problem F17-4, determine the maximum acceleration of the truck without causing the assembly to move relative to the truck. That's kind of like me driving something in my truck without it strapped down. Also, what is the corresponding normal reaction on the legs A and B? The 100 kilogram table has a center of mass G and a coefficient of static friction between the legs and the table of 0.2. So there are two ways that this could come off the truck. The first way is to slide off. The friction between the legs and the bottom of the truck is insufficient and it slides right off the back. Or the second one is for it to flip over. If the friction at B was, say, very, very high, the truck takes off, the weight of the table causes it to flip back. That moment caused by the acceleration. So let's start out with sliding. Okay, so if it starts to slide off, we'll know that the mass of the table times the acceleration of the table is equal to the normal times mu. And the mass is the normal, so ma, is mg, mu. Masses cancel. And we know that A is equal to G, 9.81, times mu, 0.2. And A is equal to 1.96. So this truck can drive without the table strapped down as long as it stays under 1.96 meters per second squared for sliding. For flipping, let's sum the moments about B. Summing the moments about B, we get, now mg is down, so that's positive. So mg times the distance 0.6. And that's causing rotation this way. The only other thing causing rotation that way would be ma, the force due to acceleration, times 0.75. Again, masses cancel, which is what we would expect. And A is equal to 0.6 over 0.75 times G, 9.81. And that is equal to 7.85 meters per second squared. So that's significantly higher than sliding. So sliding is our mode of failure. And so we'll go with the A being 1.96. So let's sum the moments about G to find the normal forces at A and B. So we got normal at B and normal at A. And I'm going to sum the moments about G. Okay, so if I sum it about G, the normal at B is causing a negative times 0.6, a negative moment. So there's our distance, normal at B. Let's draw this free body diagram over here. I've got A, or B, I've got A, and I've got G. So we have mg down. We've got normal at A, at B, normal at A, and we also have the force of friction. Now mg goes through G. We also have ma, but we don't need to worry about that. We don't have to worry about that or mg because they're both going through G. All we have to deal with is NB, NA, and F. Okay, so negative NB times 6, positive NA times 0.9, and plus the force of friction times 0.75 equals 0. Okay. So now we have, let's find force of friction. That's equal to MA. Because the only thing actually causing forward, I should change this, MA. The only one causing the forward motion is the force of friction. So the acceleration is due to friction. And so the MA is equal to the 100 times 1.96. So that's our acceleration times our mass. And that is equal to the force of friction. So the force of friction is equal to 196 newtons. Now, we need to solve force of friction. We need NA and NB. So we have two unknowns. But we also know that NB plus NA is equal to 100 times 9.81, or the mass of the table, or the weight of the table. So moving NB over here, NA is equal to 981 minus NB. Putting this in for NA and this in for F, we get negative 0.6 NB plus 981 minus NB times 0.9 plus 196 times 0.75. Distributing negative 0.6 NB plus 882.9 minus 0.9 NB plus 147 equals 0. Solving that, NB is equal to 687 newtons, and NA is equal to 981 minus that, which is 294 newtons.